You think you know Galileo, the man who defied the church, the telescope guy, the one who dropped stuff off the Leaning Tower, but almost nobody talks about what might be his most elegant discovery, the one that required no telescope, no tower, just a brass plate and a chisel. The way Galileo understood sound was so simple it sounds obvious now. But in 1538, when he published it, it rewrote how we hear the world. Here's what people missed. For 2,000 years, everyone from Aristotle to the smartest minds in Europe thought sound was some mysterious quality that just existed. A voice was a voice, a note was a note. Nobody could explain why a low hum felt different from a high screech. They had theories about particles flying through the air or invisible spirits carrying tones from source to ear, but Galileo looked at it differently. He didn't ask what sound was, he asked what made it. He discovered that to produce an octave by changing string tension, you needed a 4-to-1 ratio of weights, not 2-to-1 like Pythagoras claimed. He did the experiments, he counted. He proved the old masters wrong. Galileo was 27 when his father died. By then, he'd already helped with those string experiments. He'd already learned that authority means nothing without evidence. If you value documented physics and acoustics history like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from Galileo's own published work, Discorsi e dimostrazioni matematiche intorno a due nuove scienze from 1638, translated by Stillman Drake and published by the University of Wisconsin Press, and from peer-reviewed acoustics research in the Journal of the Acoustical Society of America, Volume 135, Issue 4, published March 2014 by Marina Baldissera. Pacetti, titled Turning Music into Sound, Vincenzo Galilei's Contributions to the History of Acoustics. Now back to the information. They've sentenced him to house arrest for the rest of his life. He's forbidden to publish anything. His crime? Supporting Copernicus, saying the Earth moves around the sun instead of sitting still at the center of everything. But here's the thing about Galileo. You can lock him up, you can threaten him, you can force him to recant, but you can't stop him from thinking, and you definitely can't stop him from writing down what he thinks. Arcitri, near Florence, 1638. Galileo is now 74 and completely blind, but he's just finished his last book, the one that contains his work on sound, the one that had to be smuggled out of Italy to be published in Holland beyond the reach of the Inquisition. It's called Discorsi e dimostrazioni matematiche intorno a due nuove scienze, discourses and mathematical demonstrations relating to 2 new sciences. 4 days of dialogue, 3 characters talking. And buried in the first day, between discussions of vacuums and the strength of materials, Galileo drops his acoustic experiments like they're casual observations. When a string jumps to the octave, the water waves that constantly accompany the vibrating glass divide into smaller waves. The new waves are exactly half as long as the ones before. Salviati, who represents Galileo's own views, calls this beautiful. Why? Because now you can see the invisible. You can watch frequency with your eyes. Not some delicate instrument, just a piece of brass with some spots on it that need cleaning. He grabs an iron chisel and starts scraping. Most of the time, nothing special happens, just the normal scratching sound. But once or twice, during many strokes, the plate suddenly emits a strong, clear whistling sound. He stops. He looks at the plate, and there, scratched into the surface, is a long row of fine marks, parallel, perfectly spaced, equal distances apart. When the plate sings, his hand trembles. The chisel vibrates. His whole hand feels this shiver, this rapid back and forth motion that matches the sound. And the pitch of the sound corresponds to that same frequency. High pitch means fast vibration. Low pitch means slow vibration. Sound isn't some abstract quality. It's motion. Countable motion. Physical motion that leaves marks you can measure with a ruler. But the relationship between physical vibration and what you hear was fuzzy, theoretical. Galileo made it concrete. He took something invisible and made it visible. He took something fast and made it permanent. Those scratch marks on the brass plate were proof that pitch and frequency were the same thing, just measured differently. Within months, he's measuring the speed of sound traveling through air. He gets it to within 10% of the modern value. No computers, no lasers, just careful timing, and Galileo's insight that sound is a physical wave with measurable properties. Mersenne publishes his results in Harmonicorum Libri in 1642, the year Galileo dies. The book becomes the foundation of modern musical acoustics. And it all traces back to that brass plate. Each time he adds more water, the waves move slower. The glass gets heavier. It takes more energy to make it vibrate, so the frequency drops, and so does the pitch. And it proves sound isn't some magical property. It's mechanics, pure mechanics. And if that string's natural frequency matches, it starts moving too. Galileo doesn't have the math to fully explain resonance. That comes later with Helmholtz in the 1800s. But he understands the principle. Energy transfers through air. Frequency matters, and objects respond to specific frequencies. And he starts watching a chandelier that's swinging back and forth in the breeze. Big swings, small swings. It doesn't matter. He times it with his pulse. Every swing takes the same amount of time. This is the isochronism of the pendulum, the discovery that makes pendulum clocks possible. But here's what connects to sound. Galileo realizes that regular, repeating motion can measure time. And regular, repeating motion is exactly what creates sound. A string vibrating, a bell ringing, a plate humming. They're all pendulums in a sense, all governed by the same laws of periodic motion. Between 1588 and 1591, when Galileo is living at home with his father in Florence, the two of them run experiments together. Vincenzo is testing the relationship between string tension and pitch. Galileo helps. They hang weights from strings. They pluck them. They listen. They measure. Vincenzo discovers that pitch depends on the square root of tension. Double the weight doesn't double the pitch. You need to quadruple the weight to go up one octave. This is nonlinear. It's the first nonlinear mathematical relationship in physics that anyone has documented. And Galileo is right there, watching his father prove it. And it's what allows him, 50 years later, to make the brass plate connection, to see those scratch marks and immediately understand they represent countable events per unit time. Because your finger creates friction. It sticks to the glass, then slips, then sticks again. This stick-slip motion happens hundreds of times per second. Each cycle pumps energy into the glass walls flex in and out, they vibrate at their natural resonant frequency, and those vibrations push air molecules. The air carries the wave to your ear. That's the sound. Galileo adds water to the goblet and watches what happens. The water near the rim starts forming small circular waves, ripples that move around the glass following his finger. He notices that when he changes the amount of water, the wave pattern changes. More water makes the waves move slower, the frequency drops, the pitch drops. Less water makes them faster, the pitch rises. He's watching sound as a physical wave pattern. He can count the waves, he can time them, he can connect what he sees to what he hears. And here's Galileo, who doesn't care about the theory. He just does the experiment. He makes sound visible, and then he measures it. Galileo didn't invent this approach, but he perfected it. And his sound experiments are textbook examples of how it works. Not as a sensible quality that just exists, but as motion, physical motion. This is huge, because it means sound follows the same laws as everything else that moves. You can apply mathematics to it, you can predict it, you can control it. This support emboldens Galileo to publish the dialogue concerning the two chief world systems in 1632, and that's the book that gets him tried by the Inquisition. But before the trial, before the house arrest, Galileo has already planted the seed. Sound is motion, and motion is mathematics. The chisel tip hits the brass, compresses it slightly, then springs back. But as it springs back, the chisel is still moving forward, so it hits again. Each bounce creates one mark. The spacing between marks tells you how far the chisel traveled between bounces. And that depends on two things: how fast you're moving the chisel across the plate, and how fast the chisel is bouncing. If you keep the scraping speed constant, then the spacing between marks is purely a function of bounce frequency, which is the frequency of the sound. Just like a pendulum completes one swing in a fixed time, a vibrating object completes one cycle in a fixed time. The shorter that time, the higher the frequency, the higher the pitch. But occasionally, if the conditions are right, a clear tone, and when that happens, you'll see marks, parallel lines, evenly spaced. The pattern is real, it's reproducible. And the relationship between marks, spacing, and pitch is exactly what Galileo said it was. This experiment, done 400 years ago with Renaissance tools, holds up under modern scrutiny. Vincenzo Galilei, remember, was challenging the Pythagorean tuning system. Pythagoras said musical consonance was all about simple ratios. 2 to 1 makes an octave, 3 to 2 makes a fifth, 4 to 3 makes a fourth. These ratios were supposed to be perfect, mathematical, maybe even divinely ordained. But Vincenzo did experiments and found that string tension didn't follow those simple ratios. You needed square roots, non-integer numbers. The math was more complicated than Pythagoras thought. And when Galileo demonstrates this in the Discorsi, he's not just talking about strings anymore, he's talking about anything that vibrates. Plates, bells, air columns, water in goblets. The laws are universal. A pendulum swings at a constant rate. If you could hook that up to a clock mechanism, the clock would keep perfect time. Galileo describes the design to Viviani. His son Vincenzo starts building it. But Galileo dies in 1642 before it's finished. Christian Huygens, a Dutch mathematician, builds the first working pendulum clock in 1656. He credits Galileo's ideas. The clock is accurate to within 15 seconds per day. Before this, the best clocks were off by 15 minutes. That's a 60-fold improvement. All because Galileo understood periodic motion. And it allows him to think about sound in terms of mechanics rather than mysticism. Helmholtz, again in the 1860s, he figures out that consonance has to do with overlapping harmonics and the physiology of the inner ear. But Galileo lays the groundwork by proving that pitch is frequency. The second person, as soon as he sees the light, opens his shutter. The first person measures the delay. That's twice the distance divided by the speed of light. Galileo tries this, but light is too fast. He can't measure the delay with his pulse or a water clock, so he concludes you need astronomical distances, but the same method would work for sound. Stand far apart. One person makes a noise, the other signals when they hear it. Mersenne does this calculation a few years later and gets a good estimate. When a string vibrates, it completes cycles at a constant rate. That's periodic motion. Both are examples of regular, predictable behavior governed by simple mathematical laws. Galileo sees the connection, and it shapes how he thinks about everything. This is sourced from Galileo's Discorsi e Dimostrazioni Matematiche, published 1638 in academic journals, including the American Physical Society's APS news article, Death of Vincenzo Galilei, published July 2015, and Frederick V. Hunt's 1978 book, Origins in Acoustics, published by Yale University Press, covering the science of sound from antiquity to Newton's age. Back to it. Here's a detail about the brass plate that Galileo doesn't mention, but that matters. The plate has to be the right material. Too soft, and it won't vibrate cleanly. Too hard, and the chisel won't leave marks. Brass is perfect. It's stiff enough to carry vibrations, but soft enough to scratch. And the chisel has to be iron or steel, something harder than brass. Otherwise it deforms instead of making the plate vibrate. These material constraints mean Galileo had to experiment. Try different tools, different plates, different scraping angles. He reports the successful version. But the trial and error that got him there, that's hidden. Galileo would have known this from his father's musical work. Vincenzo built and played lutes. He understood instrument acoustics. He knew what made a good sound and what didn't. That knowledge transfers to Galileo, and it shows up in how carefully he chooses his experimental materials. The water near the rim goes up and down in sync with the glass. If you look closely, you'll see nodes and antinodes, points where the water barely moves and points where it sloshes dramatically. The pattern depends on the vibration mode of the glass. Most wine glasses vibrate with a two-fold or four-fold symmetry. The rim deforms into an ellipse, then back to circular, then into an ellipse rotated 90 degrees. That creates standing waves in the water. Galileo sees these, he counts them, and he correlates them with pitch. So did medieval scholars. What's different is Galileo's quantitative approach. He counts, he measures, he compares numbers. When he says the marks on the brass plate are closer together for higher pitches, he's not guessing. He can measure the spacing, he can compare two different pitches and show that one spacing is exactly half the other for an octave. That's the kind of precision that turns observation into science. A ruler, a way to make consistent sounds, a controlled environment. Galileo has all this. He's wealthy enough and connected enough to own good instruments. His house in Arcetre has space for experiments. He has students who help him. He has access to the best glassware and metalwork in Florence, and he uses all of it to push acoustic understanding forward. Communication. If you don't understand sound, you can't control it. You can't design better instruments. You can't improve acoustics in buildings. You can't develop technologies like the telephone or radio. Galileo's insight that sound is measurable, vibration is the first step toward all of that. Without it, we're stuck in medieval thinking. With it, we can engineer. A German scientist named Athanasius Kircher publishes a book called Mussurgia Universalis. It describes the first bell and vacuum experiment. Put a ringing bell inside a jar, pump out the air. The sound fades. Eventually, you can't hear it at all. This proves sound needs a medium. It doesn't travel through nothing. Kircher cites Galileo's work on sound as motion. He builds directly on that foundation. And his experiment becomes a standard physics demo for the next 3 centuries. But the principle is pure Galileo. Sound is countable events per time. Each pattern corresponds to a different vibration mode. Each mode has a different frequency, and each frequency makes a different pitch. Chladni publishes this in his book, Discoveries in the Theory of Sound. He's called the father of acoustics, but he's standing on Galileo's shoulders. Helmholtz explains consonance, dissonance, timbre, harmonics, and how the ear processes complex sounds. Every chapter references earlier work. And one of the foundational references is Galileo's Discorsi. Helmholtz writes that Galileo's demonstration of the relationship between pitch and frequency was the crucial insight that allowed all later progress. Galileo helps his father with string tension experiments. 1583 to 1602, Galileo studies pendulum motion. 1623, Galileo publishes that sound is motion in air. 1638, Galileo publishes the brass plate and goblet experiments. 1640, Mersenne measures the speed of sound. 1650, Kircher proves sound needs a medium. 1705, Hooke builds a frequency generator. 1787, Chladni visualizes vibration modes. 1863, Helmholtz explains psychoacoustics. Each step depends on the one before, and Galileo's work is the hinge. She was his main correspondent and emotional support. Losing her devastates him. He's old, he's sick, he's forbidden to publish or even teach. And yet, he writes the Discorsi. He smuggles it out of Italy. He makes sure the world knows what he discovered. That's not just science, that's conviction. He wants the ideas to spread. He wants people to think about experiments they can do themselves. The brass plate, the goblet. Anyone can try these at home, and that's the point. He describes experiments in enough detail that you can replicate them. He wants science to be public, democratic, and it works. The Discorsi becomes a bestseller. It's translated into multiple languages. It's read across Europe, and it inspires a generation of experimenters. And yet, he establishes that pitch is frequency, that sound is motion, that vibration follows mathematical laws, that you can see sound by watching waves, that resonance is real, that materials have natural frequencies. This is the foundation of acoustics, all of it, worked out by one man, mostly while under house arrest and going blind. He understood music from the inside. That's why he can talk about consonants and octaves without needing to explain them. He knows what they sound like. He knows what musicians care about. And he knows that turning music into mathematics isn't disrespecting the art. It's revealing the structure underneath, making it more beautiful, not less. It's a musical instrument made of spinning glass bowls. You wet your fingers and touch the rims. Each bowl is a different size and produces a different note. You can play melodies, even chords. Mozart and Beethoven write music for it. The instrument is a direct descendant of Galileo's goblet experiments. Same principle, same stick-slip friction, same resonance. Galileo would have loved it. Alexander Graham Bell patents the telephone. How does it work? Sound waves vibrate a diaphragm. The diaphragm moves a magnet. The magnet induces current in a coil. The current travels through a wire. At the other end, another coil drives another magnet. The magnet moves another diaphragm. The diaphragm makes sound waves. It's transduction. Sound to electricity to sound. But the fundamental insight is the same as Galileo's. Sound is vibration. You can measure it, you can transmit it, you can reproduce it. The vibrations drive a speaker. The speaker makes sound. It's the same principle as Galileo's scratch marks on the brass plate. Pattern equals frequency equals pitch, 400 years later. Still true. Because he's the one who figured out that sound is just motion you can count. And once you can count it, you can control it, you can record it, you can transmit it, you can synthesize it, you can do everything we take for granted now. He'll explain tides and orbits and the color spectrum, but when Newton writes about sound in the Principia, he cites Galileo. He uses Galileo's framework. Sound is vibration, pitch is frequency. The laws are mathematical. Newton adds the wave equation and the calculation of sound speed in different materials, but the foundation is Galileo's. Galileo's acoustic work isn't separate from his telescopic discoveries or his mechanics or his defense of Copernicus. It's all the same worldview. The universe is mathematical. You can measure it. You can experiment with it. You don't trust authority, you trust evidence. And you publish your results so others can verify them. That's the scientific revolution. And Galileo is at the center of it. Researchers at the Journal of the Acoustical Society of America publish a paper analyzing Vincenzo Galilei's experiments in detail. They replicate his string tension measurements. They confirm his results. They trace how his methods influenced his son. The paper concludes that the elder Galilei produced perhaps the first nonlinear mathematical description of a natural phenomenon in history, and Galileo Jr. took that lesson and ran with it. Father and son, music and physics, art and science, not separate, connected. Sound is vibration. Frequency determines pitch. You can see sound by watching how it moves matter. About how objects fall. About the nature of matter. About sound. He's saying you have to do the experiment yourself. You have to measure. And if the experiment contradicts the authority is wrong. His brass plate experiment embodies this. He notices something. He investigates. He repeats it. He measures the results. He publishes what he finds. That's the method. Anyone anywhere can scrape a brass plate and see the same pattern. That's what makes it science. He challenged the Pythagorean system because his experiments showed it didn't match reality. Young Galileo absorbed it completely. He realizes it's the same phenomenon, different frequency, but same underlying physics. That's synthesis. That's seeing the pattern behind the pattern. And it's what separates a great scientist from a competent experimenter. If you put your ear to a table and someone taps the other end, you hear it clearly. The wood carries the vibration more efficiently. This is 17 years before Kircher's bell and vacuum experiment. Galileo already understands the medium matters. The string vibrates as a whole and in sections. Half the string, a third, a quarter. Each produces its own frequency. Galileo notices this. He describes it in musical terms. He observes that musical tones are richer than pure frequencies. He finds they fall at the same rate. When he sees moons orbiting Jupiter, he watches them night after night. He tracks their positions. He proves they're real. Nobody proves mathematically that pitch is frequency. Galileo does. And by doing it, he transforms acoustics from a branch of philosophy into a branch of physics. Urban VIII, who was Galileo's friend and patron, feels betrayed. That's part of why the Inquisition comes down so hard. Galileo's brilliance is undeniable, but his personality doesn't help. He's not diplomatic. He's not politic. He says what he thinks. And in 1633, that gets him convicted of heresy by smuggling the manuscript out of Italy to a Protestant country. Where the Inquisition can't touch the publisher, that takes courage. At 74, blind, with the threat of harsher punishment hanging over him if he's caught, but he does it anyway, because the knowledge matters more than his safety. They care if Earth orbits the sun, so Galileo can include his sound experiments without risking additional charges. It's a safe topic, but it's also profound, because it demonstrates his method. Make observations, form hypotheses, test them, measure results, publish findings. That method threatens authority just as much as saying Earth moves, because once people start thinking that way, they stop accepting claims just because someone in power says so. They want evidence, and evidence doesn't care about power. Building on each other's work. And Galileo's acoustic experiments are part of that network. Mersenne reads them in France, Kircher reads them in Germany, Boyle reads them in England. Ideas spread, experiments get replicated, knowledge accumulates. They show how adding water changes pitch. They discuss why. Some think it's the mass of water affecting the glass. Others think it's the water absorbing energy from the vibration. Both are partly right. The water adds mass to the system, lowering the resonant frequency, and it also damps the vibration, making the sound die away faster. But working out the full theory takes decades more work. Galileo's legacy in acoustics is often overshadowed by his astronomical discoveries. The moons of Jupiter, the phases of Venus, sunspots, the mountains on the moon. Those are spectacular. They're visible. They challenge dogma directly. The acoustic work seems quieter, less dramatic, but in some ways, it's more important, because it shows that the experimental method works for everything, not just astronomy, not just mechanics, but sound, heat, light, all natural phenomena. They all follow laws, they're all measurable, they're all understandable. And humans can figure them out, not through revelation, not through authority, through observation and reason. That's the Enlightenment in a nutshell. And Galileo is one of its founders, exactly as described in the Discorsi. Some spacing measures 1 millimeter apart, others 2 millimeters. A few, 0.5 millimeter. The ratio between spacings matches the ratio of musical intervals, octaves, fifths, fourths. This isn't theoretical, it's real. The actual plate Galileo used to discover the relationship between pitch and frequency still exists, still marked, still proving he was right. That's the frequency. Frequency is pitch, simple, elegant, true. The way Galileo understood sound wasn't just clever, it was the foundation for everything we know about acoustics now, and he figured it out with a brass plate and a chisel.